Welcome back everyone for another SVSU Math and Physics Resource Center tutoring video. My name is Brennan, I'm going to be your math tutor, and we're going to get into the P-series and the P-series tests, which we can use to show if a series converges or diverges. Alright, let's go ahead and get at it. Alright, let's go ahead and get into the P-series and the P-series test. So the P-series takes the form of the summation from n is equal to 1 to infinity of 1 over n to the p, where p is a constant. So here the two things that we need to keep in mind is that if p is greater than 1, we know the series converges, and if p is less than or equal to 1, we know the series diverges. And so let's go ahead and get into a few examples and we can show how those look. So our first example, we have the summation of n is equal to 1 to infinity of 1 over n to the fifth. So here our p is equal to 5, which is greater than 1, which tells us that our series converges. Okay, yeah, so that's easy enough. Now let's go ahead and go to the second example. We can rewrite this example as the summation of n is equal to 1 to infinity of 1 over n to the 1/2 power. This is just rewriting the square root as a power. And so here we know that p is equal to 1/2, which is less than or equal to 1, which tells us that it diverges. Okay, so you might be wondering, how do we know this? How do we know that if our p is greater than 1, the series converges, and if our p is less than or equal to 1, the series diverges? So the way that we know this is actually by, we can use the integral test. So let's go ahead and set up the integral test for this first example here. So this piece here is our a of n. So our f of n is equal to 1 over n to the fifth, and then our f of x is equal to 1 over x to the fifth. Okay, so we need to show that the series is positive, we need to show that it's decreasing, and that it's continuous. Okay, so if our function is ranging from 1 to infinity, and I only have positive values here, that means my function is only ever going to be positive, so we can check off on the positive. Now, decreasing, what we can do is, if we look at the denominator, we know that as x goes from 1 to infinity, our denominator is going to get bigger and bigger and bigger, which means our function is going to get smaller and smaller and smaller because our numerator isn't changing. So, yep, we can check off the decreasing part. And then now we need to show that it's continuous. So the only point that this function is discontinuous is when our denominator is equal to 0. So that would be x is equal to 0. But our interval is ranging from 1 to infinity. So we know we're continuous on the interval. Okay, so we can go ahead and check that last one off, and then we can go ahead and run through the integral test real quick. So the integral test says that we can write this out as an improper fraction. So this needs to be 1 to infinity of our function, which is 1 over x to the fifth dx. So this is our improper integral that we want to see if it converges or diverges. So we can rewrite this out with a limit as t approaches infinity. And if you haven't already checked out the integral test videos, I recommend going through and checking those out before checking out this kind of proof for the p-series. So this is going to be the integral from 1 to t. We're replacing the infinity with the t. And I'm going to go ahead and rewrite this as x to the negative fifth dx. Okay, so let's go ahead and solve this integral. So this is going to be the limit as t approaches infinity. Let's see, so this looks like it's just going to be the power rule. So we're going to go ahead and raise the power by 1, so that's going to become negative 4, and then we're going to divide by the new power. So we'll end up with a negative 1 over 4 x to the negative 4, evaluated from 1 to t. Okay, so let's go ahead and evaluate this. So it's going to be the limit as t approaches infinity of negative 1 over 4. And then this is going to be t to the negative fourth minus 1 to the negative fourth. Okay, so then I want to come up here. Let's go ahead and simplify this. It looks like we're going to end up with the limit as t approaches infinity of negative 1 over 4, 1 over t to the fourth minus, and so 1 to the negative fourth is just 1 over 1 to the fourth, and so that's just going to end up being 1. Okay, so now let's go ahead and evaluate the limit. So let's plug in our infinity. So when we plug in the infinity here, we're going to get infinity to the fourth, but it's on the denominator, so that tells us that this piece is going to go to 0. So it looks like this is all just going to go ahead and be equal to negative 1/4 times negative 1 is going to be 1/4. And so then that tells us that this improper integral converges to 1/4, so we know that our series should also converge, which is the same thing that the p-series test showed us. Okay, so just remember, if you're working with a p-series, it has to be in this form, and if your p-value is greater than 1, your series converges, and if your p-value is less than or equal to 1, your series diverges. So the p-series is going to end up being very, very useful when we get into the limit comparison test and the direct comparison test. All right, thanks for watching.